Bismillahirrahmanirrahim. Hi everyone. I hope you are all doing well. I welcome you all in class of real analysis. In today's lecture, we will discuss absolute value of a complex number, that is also called modulus of complex number, and some properties related to absolute value of complex number. So firstly, we define what is the definition of absolute value of complex number. Uh, if z is a complex number, then its absolute value is denoted by z absolute. It is the square root of this product z into z conjugate. So this is the definition that is given in this textbook. So z absolute or z modulus is the square root of z into z conjugate, or you can write as square of z absolute is equal to z into z conjugate. If z is a some particular number a plus b iota, then its absolute or modulus can be defined as square root of a square plus b square. Geometrically, you know the z absolute or modulus of z is the distance of the point AB from the origin in the complex plane. Next, we discuss theorem 1.33. If z and w are the two complex numbers, then prove that the absolute value of z is always positive. It is 0 unless z is equal to 0. The second property is the absolute of z and absolute of conjugate of z is always equal. The absolute of the product of two complex number is equal to the product of their absolute value. Real part of z is absolute of real part of z is always less than or equal to absolute of z. The last one is called the triangular inequality. Z plus w, absolute of z plus w is always less than or equal to absolute of z plus absolute of w. So this is one of the important property that we will discuss at the end. First, we show that z absolute is always positive unless z is equal to 0. I am assuming a particular value of z is equal to a plus b iota, where a and b are real numbers. Then you know z modulus or z absolute is square root of a square plus b square. As z absolute is the square root of sum of squares, as you can see here, this quantity a square plus b square is this quantity is called sum of squares, and this is the square root of sum of squares, which is always positive for all ab are non-zero. And in case if ab are 0, then your modulus in case of a and b are 0, this becomes 0 square plus 0 square, which is equal to 0. Then in this case, absolute of that is equal to 0. That is required. In the second part, we have to show that modulus conjugate of z absolute, conjugate of z absolute, absolute of z conjugate is equal to conjugate of z. You can prove this property again by assuming any specific value of z, like z is equal to a plus b iota, and finding by z conjugate, which is equal to a minus b iota. And now you can take the absolute value or modulus of both numbers. You can prove that in both cases their absolute value is equal. I am using the definition given in the book as z absolute is equal to square root of z into z conjugate. So by replacing z is equal to z conjugate in this definition, we have conjugate of absolute value of z conjugate is equal to z conjugate into conjugate of z conjugate. As the double conjugate of z is equal to z, so this becomes simply z and this product z into z conjugate is again square root of z into z conjugate is again z absolute. So absolute of z conjugate is equal to absolute of z. In the next property, we have to show the absolute value of the product z into w is equal to product of their absolute value. As z absolute is equal to z into z conjugate, this implies for a complex number w, we can write it as square root of w into w conjugate. As z and w both are the complex number, so the product of two complex number is again a complex number. So I can use the definition for this product as z absolute value of z is equal to z into z conjugate. So replace z is equal to z into w. So put in this definition z is equal to zw, we have z into w conjugate of z into w. By separating the conjugate, this is the property of conjugate. This can be written as conjugate of z into w conjugate. By rearranging the complex number, we can write it as z into z conjugate and w into w conjugate. As z into z conjugate is the square of z modulus, and this is the square of w modulus. By separating the square root, we can write it as this is, by cancelling out, this is z modulus and this is w modulus. In the next property, we have to show the absolute value of a real part of z is always less than or equal to absolute value of z here. Let z is equal to a plus b iota, then you can see here the real value of z is a. This is the real part of z. Since for all a b belong to r, the square of a is always less than or equal to a square plus b square. You can choose any value of ab. You can observe that the square of a square is always less than or equal to a square plus b square. Taking square root on both sides, this becomes this is equal to absolute of a, because in case a is negative, then the square root is equal to minus a, and if a is positive, then the square root is positive a. So we can write it as in the form of absolute, and this is the definition of z modulus. As a is the real part of z, so replace a is equal to real part of z, hence real part of z, absolute value of real part of z is less than absolute of z. Next one, last property, the absolute value of z plus w is always less than or equal to sum of their absolute value. By definition, we know that the square of absolute value of z plus w can be written as z plus w into z plus conjugate of z plus w. As you know, square of z modulus is equal to z into z conjugate. So in this property, we replace z by z plus w. We have this equation. Now by using the definition of conjugate, we can separate the conjugate over these two complex number. By multiply these complex number, we have z into z conjugate, z into w conjugate, w into z conjugate, w into w conjugate. As this is equal to square of z modulus, and this is equal to square of w modulus, and these two terms are remaining same. If you observe these two terms are the conjugate of each other. How? As z and w both are the complex number, if you take the conjugate of this complex number, this is equal to z conjugate into conjugate of w conjugate. As the double conjugate of w, this is equal to simple w, and this is equal to z conjugate. So these two terms are the conjugate of each other, and we know that there is a property, if we add a complex number with its conjugate, this is always equal to 2 times real part of z. As these are both the complex number and also conjugate of each other, So when we add the conjugate, this is if we take this is the conjugate of the first one, then its sum will be 2 times real part of z into w. So replace this sum by 2 times real part of z into w conjugate in 1. This is our question number 1. So replace this sum by 2 times real part of z into w conjugate. So we have this identity, this equation. Again, by using d, we have proved that the absolute value of real part of z is always less than or equal to absolute of z. This implies real part of z into w conjugate is less than or equal to conjugate of modulus of z into w conjugate. So put this inequality in 2 implies 2 implies square of z plus square of modulus of z plus w is always less than or equal to square of z modulus plus square of w modulus plus 2 times z into modulus of z into w conjugate. Again, by using the result, we can separate both of the product of both of the complex numbers z into w conjugate is equal to z modulus of z into modulus of w conjugate, and the modulus of w conjugate is equal to modulus of w. So the last term, this term, can be written as 2 times z modulus into w modulus. This is the square of modulus of z plus w modulus. Taking square root on both sides, we have the required result. So in this short video, we have discussed about the modulus or absolute value of complex number and some important properties related to them. Inshallah, in the next lecture, we will discuss a very important inequality, that is Cauchy-Schwarz inequality. So if you find this lecture is helpful, kindly like, share and subscribe. See you in the next lecture. Take care. Allah Hafiz.